Every dominant sunspot the sun has built this summer has followed the same script. 3 days of violent eruptions, then silence. The monster at the centre of the solar disk was born 2 days ago, and instead of winding down on schedule, it fired the strongest blast of its life this morning, blacking out radios across the Americas before dawn. It now carries a 1 in 10 daily chance of an X-class eruption, the most powerful kind our star produces, while aimed almost directly at Earth, with a storm of fast solar wind arriving tonight on top of it. The last time humanity misread a moment like this, in 1967, we nearly went to war over it. So the next 36 hours come down to one question. Does this sunspot fade on schedule? Or is the script about to break? If this has you watching the sky differently, hit like and subscribe. We track this star every single day. And drop a comment with where you're watching from and whether you've ever caught the aurora at your latitude. If you're far enough north, tonight might be your chance. Now let's get into it. Part 1. The clock started. 2 days ago. Just before sunrise over the Americas this morning, at 6:35 Universal Time on July 22nd, the largest sunspot region on the face of the sun released its strongest eruption yet. An M3.6 solar flare, a burst of X-ray energy that crossed 93 million miles of space in 8 minutes and 18 seconds and slammed into the upper layers of Earth's atmosphere. Radio operators across North and South America felt it before most of the continent had finished its first cup of coffee. High-frequency signals faded, crackled, and in some bands simply disappeared. A radio blackout, courtesy of a knot of magnetism on the surface of our star that did not even exist 3 days ago. That last part is the detail that should stop you. This region, catalogued as Active Region 4493, was born on July 20th, not discovered, born. It erupted out of the sun's interior almost dead center on the disk as seen from Earth, assembled itself into a monster in roughly 18 hours, and started firing almost immediately. We covered its birth 2 days ago, in our video on the sunspot the sun was building in real time. At that point the question was what this thing would become. Today we have the answer, and we also have something more unsettling, a deadline. Because there is a pattern here, a pattern that solar observers have been tracking through this entire stretch of the solar cycle, and one that this channel has watched play out 3 times in the last month alone. The dominant sunspot regions of this era, the big, complex, magnetically twisted groups that seize control of the sun's activity for a week at a time, have been following the same script. They emerge fast, they erupt hard, they run roughly 3 days of hyperactivity hurling flare after flare into space, and then, almost on cue, they settle down, they stabilize, the fireworks stop, the magnetic knots relax, and the region that looked like it might throw the biggest punch of the year quietly rides the sun's rotation off the western edge of the disk and is gone. 3 days of fury, then quiet. That is the pattern. And if it holds for active region 4493, then the math is very simple and very uncomfortable. The region emerged on July 20th. Day 1 was July 20th itself, 4 eruptions of M-class or near it. Day 2 was yesterday, July 21st. Day 3 is today, which means the window in which this region does whatever it is going to do, the window in which it either fires the biggest eruption of its life or begins its slide into quiescence, is the next 36 hours. That window is open right now. It closes sometime tomorrow night into early July 24th. And here is what makes today different from every previous time this pattern has played out. This region is not slowing down on schedule, it is speeding up. The M3.6 that darkened radios this morning was not a leftover, not a dying gasp from a region winding down. It was the strongest flare this region has ever produced, delivered on the exact day the pattern says the fury should be ending. Think about what that means for a moment. Either the pattern is about to break, and this region is something the recent script does not describe, or the peak release is still ahead of us, somewhere inside the next 36 hours, from a sunspot group that is currently aimed almost directly at this planet. That is the story of this video. Not a prophecy, not a doomsday countdown, a genuine scientific cliffhanger, unfolding in real time, with the clock already running. And I want to be precise with you up front, because precision is the whole game here. The official numbers, published this morning by NOAA's Space Weather Prediction Center, give this region a 50% chance of more M-class flares each day through July 24th, and a 10% chance of an X-class flare, the top tier of solar eruptions, on each of those days. 10% per day is not a prediction of catastrophe. Most likely no X-flare happens at all, but 10%, repeated across the days this region stays pointed at us, adds up to real odds. Roughly 1 chance in 4 that the strongest class of solar eruption fires before this window story ends. From point-blank alignment, and there is one more layer stacked on top of tonight, because the sun rarely does one thing at a time. While this sunspot burns through day 3 of its life, a completely separate solar structure is about to arrive at our doorstep. 4 days ago, we covered the 400,000-mile-wide hole that had opened in the sun's atmosphere. A coronal hole, a gap in the star's magnetic field where solar wind pours out at extreme speed. That wind has been crossing space toward us ever since. Tonight, between 2100 Universal Time and midnight, it hits. Forecasters expect the solar wind speed at Earth to jump from around 420 km per second to somewhere between 600 and 700 km per second, enough to spark a minor geomagnetic storm, a G1 on NOAA's 5-step scale, with aurora pushed down toward the northern tier of the United States and Canada, summer twilight permitting. A minor storm on its own is routine. We will put it in its place later because this channel does not inflate storms to scare you, but the timing deserves your attention. Tonight, Earth gets hit by the wind from one solar structure while another one, loaded, growing, and escalating, stares down at us through its most dangerous window. 2 independent phenomena, 2 different kinds of solar violence, overlapping in the same 48 hours. If active region 4493 does erupt in a big way while that high-speed wind is streaming past us, the physics of what arrives here and when gets genuinely complicated, in ways scientists have studied for decades and still struggle to forecast. We will walk through exactly why. So here is where we are going. First, we need to look at this sunspot properly, at what it actually is, at the strange magnetic anatomy that makes forecasters put a number like 10% X-class on it, and at what has changed in the 2 days since it was born. Then the pattern itself, where this 3-day rhythm comes from, whether it is real physics or a small sample coincidence, and what it means that this region is violating it in the most ominous direction possible. Then tonight's storm, and the collision physics of what happens when an eruption and a windstream share the same highway to Earth. And then, in the back half of this video, I'm going to tell you a story that I have wanted to tell on this channel for a long time. A story about another enormous sunspot group, another radio blackout, and a morning in May of 1967 when the United States military, watching its early warning radars go blind, concluded that a nuclear attack might be underway. It is the story of how close the world once came to war because of exactly the phenomenon that brushed across your radio this morning, and of the handful of forecasters who stopped it. It is, I would argue, the single most important solar storm story of the 20th century, and almost nobody knows it. Because the reason we can sit here tonight, calmly watching a loaded sunspot tick through its critical window, instead of panicking at every blackout, is that 59 years ago, we learned, nearly at the cost of everything, what happens when you cannot tell the difference between the sun and an enemy. That is the journey. A sunspot on a deadline, a storm arriving tonight, and the day the sun almost started World War III. Let me give you the rest of today's dashboard before we go deeper, because the numbers set the stage with a precision no adjective can match. As of this afternoon's data, the official blackout forecast stands at a 55% chance of R1 to R2 radio blackouts on each day through July 24th, meaning more mornings like this one are now the expected outcome, not the surprise, and a 10% daily chance of R3 or greater, the level at which high-frequency radio dies across the entire sunlit side of the planet for an hour or more. The radiation environment tells its own quiet story. The proton flux that would signal a solar radiation storm is sitting at background, a fraction of a single flux unit against a threshold of 10, and the official chance of even a minor radiation storm holds at just 5% per day. But read the fine print on that 5%, because the forecasters wrote it down in plain language. The chance exists, they note, primarily due to the event potential of this one region. Even the quietest gauge on the board is quiet only conditionally, quiet unless region 4493 does the thing everyone is watching for. And the wider sun makes the concentration of threat almost eerie. There are 4 numbered sunspot regions on the Earth-facing disk this afternoon, The other three are, by every measure, spent or trivial. One, an aging, magnetically simple patch showing signs of breaking apart. Another, a small group carrying at most a 1% chance of a major flare. The third, quietly decaying toward the western edge. Between the three of them, they could not muster a single respectable eruption. Every percentage point of M-class risk, every point of X-class risk, every watt of this week's danger belongs to one address on the Sun. In 30 years of watching, forecasters will tell you that kind of monopoly is not the normal shape of an active Sun. It is the shape of this strange, top-heavy phase of the cycle, where the star goes quiet everywhere except one place, and pours everything it has into that place. Keep one more July memory in your pocket as we go, because it is the context that makes this week the rule and not the exception. On June 30th, a different Delta-class giant fired an X-1.1. On July 4th, another fired an X-1.3. Both of those regions ran hot for a few days, went quiet, and left the stage. They were the last two dominant regions before this one. The same script, the same arc, the same ending. Region 4493 is the third act of a play we have watched twice this month. The only question is whether it has read the same ending as the first two acts, and everything you are about to see suggests it may be improvising. But before any history, you need to understand the machine at the centre of this. Because active region 4493 is not just a dark spot on the Sun, it is one of the strangest and fastest growing magnetic structures this solar cycle has produced, and the forecasters who watch it have been playing catch-up since the hour it was born. What they found when they mapped its magnetic field is the reason this video exists, and the reason that 10% number may be doing a lot of quiet work. Part 2. Anatomy of a Monster. Picture the surface of the Sun as an ocean of boiling plasma, churning at around 10,000 degrees Fahrenheit, with magnetic field lines threading through it like ropes of invisible steel. Most of the time, those ropes stay below the surface, carried along by currents deeper in the star, but sometimes a great tangle of magnetic rope becomes buoyant, lighter than the plasma around it, and rises. When it breaks the surface, it punches through in pairs of dark patches where the field is so intense it chokes off the normal churning flow of heat. Those dark patches are sunspots, and when an enormous twisted bundle of them punches through all at once, you get what erupted onto the disk on July 20th. Active region 4493 came up fast even by the standards of a fast phenomenon. Most of its growth happened within about 18 hours, a monster assembling itself between one workday and the next. By this morning's official analysis, it spans 380 millionths of the visible solar hemisphere. That unit sounds small until you convert it. The visible hemisphere of the Sun is about 1 trillion square miles, and this region covers enough of it to swallow Earth several times over, with 18 individual spots counted inside its boundaries. 2 days old, and already the largest and most complicated magnetic structure on the entire Earth-facing side of the star. This is the machine ticking through the 36-hour window we opened this video with, so it matters enormously what kind of machine it is. Forecasters classify sunspot groups by their magnetic architecture, and the classifications read like escalating threat levels. A simple region is called alpha, one patch of magnetism, one polarity, like a single bar magnet's north pole poking through the surface. Beta means two polarities, north and south, arranged side by side in an orderly way. Beta gamma means the polarities have become mixed, tangled together instead of politely separated, and then there is the designation that makes solar physicists sit up straight. Delta. A delta configuration means that opposite magnetic polarities, north and south, plus and minus, are packed together inside the same penumbra, the outer skirt of a single spot so close that their field lines press directly against each other with nowhere to go. If a beta region is two magnets on a table, a delta is two magnets forced together the wrong way and welded into the same casing while they strain against each other. Active region 4493 is classified beta-gamma delta, and not with a single delta. This morning's forecast discussion from the Space Weather Prediction Center notes that the region has continued to show, in their words, growth and consolidation, while maintaining several delta magnetic configurations within its intermediate and trailing spots. Several. Multiple welded together pressure points, each one a place where oppositely directed magnetic fields are grinding against each other, storing energy the way a bent steel bar stores energy. The flares this region keeps producing, and we will walk through the full arsenal it has fired in the next part, are those pressure points slipping. The question that defines our 36-hour window is whether the slipping relieves the strain gradually or whether one of those welds fails all at once. It is worth pausing on what you would actually see, looking at this thing through a properly filtered telescope, because the darkness of a sunspot is one of the great optical illusions in nature. The spots appear black only by contrast. The umbra, the dark core of a spot, still glows at around 6,000 degrees Fahrenheit. It looks dark solely because the surrounding surface burns nearly 4,000 degrees hotter. Cut a sunspot out of the sun and hang it alone in the night sky, and it would blaze brighter than the full moon. What you're really looking at in those dark cores is magnetism made visible. Field bundles so strong, thousands of times stronger than Earth's surface field, that they throttle the rising currents of hot plasma beneath them, refrigerating a patch of star in real time. The spot is a wound the magnetic field punches in the sun's ability to deliver its own heat. Around each dark core spreads the penumbra, the fringe of combed filaments where the field splays outward, and it is inside that fringe, in the official spot class shorthand, that this region earns its menacing letters. The designation EK, for the record, unpacks into a specific portrait, a large bipolar group stretching more than 10 degrees of solar longitude, its principal spots wrapped in mature penumbrae, with the trailing section elongated and complex rather than clean. Translation: big, developed, and messy in exactly the wrong way. There is history behind that fear. Delta regions are rare, by some long-term counts. Far fewer than 1 in 10 sunspot groups ever develops one, but they produce the overwhelming majority of the sun's most powerful eruptions. The great flares that punctuate every solar cycle, the ones that make history, come almost exclusively out of delta configurations. That is why the classification alone, before you count a single flare, is enough to put a region on every watch list on Earth. When the region carrying it is also the largest thing on the disk, growing, and parked near the centre of the Earth-facing hemisphere, the watch becomes something closer to a vigil. And this particular region carries a genuine oddity on top of its complexity, one we flagged when we covered its birth 2 days ago. Sunspot pairs on the sun normally emerge tilted in a predictable way, the leading spot slightly closer to the equator than the trailing spot, a rule of thumb that has held across more than a century of observations and is known as Joy's law. It is one of those quiet regularities that tells you the sun's interior has order beneath the chaos. Region 4493 broke it. Its main polarities came up oriented roughly north to south, rotated sideways relative to what a textbook emergence should look like, an arrangement rare enough that seasoned observers publicly remarked they could not recall a recent comparable case. Add the rotation that was measured in part of the region as it emerged, a twisting motion winding the overlying field like a crank, and you have a structure that came out of the sun's interior, already stressed, already misaligned, and still being wound tighter. Now stack the timeline against the anatomy, because this is where the central tension of this video sharpens. On the morning of July 20th, hours after this region first appeared, the official forecast gave it only a slight chance of producing M-class flares at all. It produced one that same afternoon. By that evening it had produced 3 more significant eruptions. The forecast was not wrong so much as outrun. The region was evolving faster than the daily forecasting cycle could track. 2 days later, the numbers have caught up to the threat. 95% chance of C-class flares, 50% chance of M-class, 10% chance of X-class, per day, renewed each day through July 24th. Those are among the most aggressive probabilities pinned on any region this summer. Every one of those percentage points belongs to this single knot of magnetism. The rest of the visible disk, and there are 3 other numbered regions on it right now, contributes almost nothing. One region holds every card. There is a final piece of the anatomy worth carrying forward because it complicates the simple story of a bomb waiting to go off. When this region was born, analysts noted something crucial about its structure. The eruptions it produced were impulsive, sharp, short, violent, but they were not launching material into space. No coronal mass ejections could be linked to those first flares. The interpretation, which we explored in the birth video, is that the region sits inside a kind of magnetic cage. The newer, unstable fields at its core are pinned beneath older, larger loops of magnetism arching over the whole structure. The core can snap and flare, but the overlying cage catches the eruption before it can escape the sun entirely. A region like that can hold X-class energy, and independent analyses concluded this one likely already does, while releasing it only in muffled bursts. Set this region beside its neighbours and the monopoly becomes visual. Region 4492, up in the northeast quadrant, is actually the second largest thing on the disk at 250 millionths. But it is magnetically simple, a single polarity relic, and this morning's analysis noted its main spot may be undergoing umbral separation, the core splitting, the first stage of falling apart. It carries a 5% M-flare chance. Region 4494, low on the eastern side, is a modest young beta group at 60 millionths, growing slightly, threat level near nil. Region 4489 is decaying quietly toward the west. 4 regions share the disk. One of them holds 18 spots, every delta core, and effectively all of the danger. The sun this week is not broadly active. It is narrowly intensely active. One fist, clenched, at the centre of an otherwise open hand. Muffled so far. Cages on the sun are not permanent. They weaken as the region beneath them evolves, and a core that keeps flaring is a core testing its bars over and over. If the cage holds through the window, this region may spend its fury in a drumbeat of contained M-class flares, dramatic for radio operators, harmless to nearly everyone else. If the cage fails while the region is still carrying its stored energy, the result would be a full eruption, flare and coronal mass ejection together, 1 billion tons of magnetized plasma thrown off the sun. And the direction it would be thrown is the part of this story we have not fully confronted yet, because the one thing this region has that no amount of magnetic complexity can change is its address. It came up almost exactly in the middle of the disk we see from Earth. We are not watching this window from the side. We are standing at the end of the barrel, and in part 6 we will put hard numbers on exactly how long that alignment lasts. But first, the eruptions themselves. 5 significant flares in 48 hours, each one a data point in the pattern this video hangs on, and each one felt in a small way on this side of the 93 million mile gap. To judge whether the next 36 hours end in silence or in the flash this region has been building toward, you need to see what it has already done. Part 3. 5 eruptions in 48 hours. Run the tape from the beginning, because the sequence matters as much as any single blast. July 20th, 1436. Universal time, an M2.5 flare, the region's first major eruption, arriving hours after that morning's forecast had offered only a slight chance of anything M-class. July 20th, 1920. Universal time, an M1.1. July 20th, 2225. Universal time, an M3.4. 3 significant eruptions inside 10 hours, from a region less than a day old. July 21st, 1727. Universal time, an M1.9. And then this morning, July 22nd, beginning at 6:27 and peaking at 6:35 universal time, the M3.6. 5 M-class flares in roughly 40 hours, capped by the strongest of the series on what the pattern says should be the final day of fury. To make sense of those numbers, you need the scale. Solar flares are ranked by the intensity of their X-ray output, in lettered classes that step upward by factors of 10. A, then B, then C, then M, then X. Each letter is 10 times the one before it, and the number refines the position inside the class. An M2 is twice an M1. An M3.6 is 3.6 times an M1. C-class flares are background noise, barely felt at Earth. M-class flares are the middle heavyweights, strong enough to disturb the ionosphere on Earth's daylit side, strong enough to matter to radio operators and polar flights. X-class is the top of the ladder, the class of the historic events, and an X1 is roughly 2.8 times stronger than the M3.6 that opened this morning. The ladder keeps going. An X10 is 10 times an X1. But the important point for our window is that this region is now punching at the upper middle of the scale and trending upward, with forecasters holding a 1 in 10 daily chance that it takes the final step. Now, what actually happened when this morning's flare reached us, because something did happen on this side of the gap to real signals in real time. A solar flare is a flash of electromagnetic radiation, and the X-ray and extreme ultraviolet portion of that flash does something specific to our planet. It slams into the upper atmosphere 60 to 90 kilometers up and rips electrons off the atoms it finds there, flooding a layer called the ionosphere with far more charge than it normally carries. That matters because the ionosphere is not just a passive shell, it is the mirror that long-distance radio depends on. High-frequency radio, the band used by transoceanic aircraft, ships, emergency services, and amateur operators around the world, travels beyond the horizon by bouncing between the ground and that charged layer. Change the layer and you change the mirror. Overcharge its lowest region, and instead of reflecting radio waves, it absorbs them. Signals that should skip halfway around the planet simply die in the sky. Who actually lives on those frequencies in the satellite age? More people than you might guess. Transoceanic and polar airline flights carry high-frequency radio as their primary long-range link precisely where satellite coverage thins near the poles, which is why significant blackouts push polar routes toward lower latitudes, adding fuel and hours. Ships beyond coastal range, military networks built for resilience, disaster response teams operating where towers are down, and the global community of amateur operators who provide emergency backbone when infrastructure fails, all of them bounce signals off the layer this region keeps bruising. A flare's ultraviolet surge also puffs up the ionosphere's higher layers, nudging the single-frequency satellite navigation solutions used in surveying and agriculture by meters. None of this is catastrophic at the M-class level. All of it is real, physical contact between that spot group and the working systems of this planet, repeated now 5 times in 2 days. That is a radio blackout, and it is not an abstraction. It happened this morning. As the M3.6 peaked, NOAA registered an R1 radio blackout across the entire sunlit hemisphere of Earth, which, at 6:35 Universal Time, meant the Americas. R1 is the bottom of a NOAA's 5-level blackout scale. Degradation of high-frequency communication on the daylit side, dropouts lasting tens of minutes, weak, brief, routine, and detected from Maine to Chile all the same. Yesterday's M1.9 did the same thing at a lower intensity. This is now a region that has repeatedly reached across 93 million miles and touched infrastructure on our planet, and every escalation on that flare ladder deepens the touch. An R3 event, the level the forecasters currently hold at 10% probability per day, the level an X-class flare typically produces, means wide area loss of high-frequency communication across the sunlit side for an hour or more. Hold that thought, because the entire second half of this video turns on what happens when the people relying on those frequencies do not know the sun is the reason they went quiet. This morning's flare carried a second signature worth understanding, one that connects directly to that second half. Alongside the X-ray flash, the eruption produced what solar physicists call a 10-centimeter radio burst, a 2-minute scream of microwave static, peaking at 200 solar flux units against a quiet sun background of about 149. In plain terms, for 2 minutes, the sun became a radio transmitter shouting at more than double its normal volume in the band that radars and communication systems share. 200 flux units is modest, a murmur as these things go. But file away the concept of the sun as an unlicensed broadcaster stepping on human frequencies, because later in this video you will meet a burst that measured not 200, but 373,000, and it very nearly changed history. One gauge, meanwhile, has stayed mercifully flat through all 5 eruptions, and it is worth naming because it guards the most vulnerable humans in this story. The proton monitors, watching for the swarms of accelerated particles that constitute a solar radiation storm, have not budged, flux holding at a fraction of a single unit against a storm threshold of 10, the radiation scale pinned at S0 throughout. Radiation storms are the space weather hazard that matters most to astronauts, to polar flight crews, and to satellite electronics, and this region has so far produced none, because its flares, for all their snap, have been brief and structurally contained. The forecast keeps the odds of even a minor radiation storm at 5% per day low, but attributed in writing to this region's event potential, and it is the number that would move first if the character of these eruptions changed from contained to eruptive. A 5th quiet gauge is not nothing. It is also not a promise. There is one more reading on the instruments that deserves your attention, and it is in some ways the strangest of all, the background level. Between eruptions, the sun's X-ray output from this region does not fall back to quiet. It has been idling around the C1 level all day, meaning that even in the gaps between flares, this single region keeps the whole sun's X-ray output simmering at what would, in a calm month, count as a minor flare in progress, around the clock. A pot that never stops boiling. The latest bubble, a C3 flare just after noon, Universal Time today, barely rates a mention on a normal day. On day 3 of this region's life, it reads as a metronome, the strain inside those delta cores releasing in tick after tick while the window runs down. Set the whole sequence side by side and you can see the shape of the problem the forecasters are staring at tonight. Day 1, 4 eruptions, fast and stacked. Day 2, 1 eruption, and a region that some might have hoped was settling early. Day 3, the strongest eruption of the sequence before breakfast. This is not the profile of a region relaxing into quiescence. Plot those flares on a chart and the trend line through them points up and to the right, directly into the 36 hours during which, if the recent pattern of dominant regions means anything, this region's story has to resolve. Escalation and deadline converging. And notice what is missing from everything the region has thrown so far. The absence that has quietly kept this story from becoming an emergency. 5 M-class flares and not one confirmed eruption of material aimed at Earth. The cage, as far as anyone can tell, is holding. The flashes escape. The mass does not. Yesterday brought the first hint that this might be changing. At 10:45 Universal Time on July 21st, a filament of cool, dense plasma, one of those dark magnetic ropes that hang suspended above the solar surface, erupted just to the northwest of the region. A few hours later, coronagraphs watching the space around the sun picked up a faint puff of ejected material heading off the northwest edge. As of the most recent forecast discussion, modelers were still working to determine whether any component of that ejection is heading toward Earth. It is probably nothing. Faint, off-axis, glancing at worst. But it is the first time in this region's short life that the words coronal mass ejection and Earth-directed have appeared in the same sentence of an official product, even as an open question. An open question is exactly what it remains, and it sits at the end of a chain of them. Why do regions like this burn for 3 days and then stop? Is that pattern physics, or coincidence wearing the costume of physics? And what does it mean that this region is reading from a different script? That pattern is the clock this entire video runs on, so it is time to take it apart and see whether it actually keeps time. Part 4. The 3-day pattern. Real clock or coincidence? Every gambler knows the feeling of seeing a pattern in the cards. The question that separates science from superstition is whether the pattern survives being counted. So let us count, carefully, honestly, because the claim at the centre of this video deserves better than either blind belief or a lazy shrug. The claim, as it has spread through the community of solar watchers this week, goes like this. The recent dominant sunspot regions, the ones that take over the disk and drive the sun's activity for a stretch, have each displayed roughly 3 days of hyperactivity, throwing powerful flares before stabilizing into relative quiet. If that holds for the current region, then the next 36 hours are the most critical. That framing has been circulating widely online, and versions of it are the reason phrases like critical window are attached to this region at all. This channel did not invent the claim, and you should know exactly how much weight it can bear. Start with the cases you have watched yourself if you have been following this channel through July. In the last week of June, a pair of Delta-class regions rose to dominance together. We covered them at the time as the double Delta event. Flagged as they turned complex around June 25th, they peaked with an X 1.1 flare on June 30th, and a barrage of M-class flares around the turn of the month, and within days had faded from headline threat to background feature. In early July, another region seized the spotlight and delivered the X 1.3 of July 4th, and then it too quieted and carried its remaining strain around the western limb. Earlier this month we called that stretch the sun that would not stop firing. Each time the arc was the same, a violent adolescence measured in days, then a long quiet middle age. 3 bursts of dominance, 3 fades. Now comes region 4493, the third dominant delta structure in 4 weeks, running the same opening act on an even faster clock. Is there physics underneath that arc, or only coincidence? Here the honest answer is some of both, and it pays to know which is which. The real physics is the life cycle of magnetic flux emergence. A sunspot region is violent while it is being built. During emergence, new ropes of magnetic field are still surging up from the interior hour after hour, crashing into the fields that surfaced before them, forcing rearrangements, and every forced rearrangement is an opportunity for the short-circuit process called magnetic reconnection, which is what a flare actually is. Statistical studies of thousands of regions bear this out. Flare productivity clusters during and just after the emergence phase, while the magnetic architecture is still under construction, and the gradients between opposite polarities are steepest. Once emergence tapers off, the region begins to relax. The polarities drift apart, the sharp boundaries soften, the stored energy bleeds away in small events or simply stops accumulating. Fast emerging regions tend to burn hottest precisely because their construction phase crams the most collisions into the least time. A region that assembled itself in 18 hours, like this one, is the extreme case. Maximum construction violence, compressed. So the 3-day rhythm is not mystical. It is roughly the timescale on which a fast-emerging region finishes building itself and begins to settle. That much is textbook. What is not textbook, and this is where intellectual honesty has to bite, is the precision. 3 days is not a law. It is an average drawn from a handful of recent cases, and a handful is the operative word. Regions exist that emerged, quieted, and then reorganized into a second act deadlier than the first. Regions exist that stayed violent for 2 full weeks. The most notorious counterexample sits in the historical record of September 2017, when a region catalogued as 2673 spent days as a modest, unremarkable spot group, and then, in its second phase of growth, transformed within about 48 hours into the source of the largest flares of that entire solar cycle, an X9.3 among them, fired when the cycle was supposedly in decline. We told that region's story 2 days ago in the birth video, and it hangs over this window like a warning label. The pattern describes what usually happens. It does not constrain what can happen. The 2017 case rewards 1 more minute of attention, because its details map onto this week with uncomfortable precision. That September, the sun was 3 years past its cycle peak, deeper into decline than we are now, and the sunspot number was scraping lows. Region 2673 began its disk crossing as a small, simple group that most forecasts rated modestly. Then new magnetic flux began surging up beneath it, and within about 2 days its area had grown several-fold, and its configuration had knotted into exactly the class of structure our current region wears: beta-gamma-delta, multiple welded cores. What followed was the most violent week of the entire cycle. Dozens of M-class flares, 4 X-class events including the X9.3, the largest of the cycle, and days later, an X8.2 fired from the very edge of the disk as the region departed. The lesson encoded in that sequence is the one that keeps tonight's window honest in both directions. A region's past behaviour constrains nothing once fresh flux starts rising, and the difference between a fading spot and a cycle-defining monster can be a single unseen surge from below, hours in the making. Growth is the tell, which is why the phrase in this morning's official discussion, continued growth and consolidation, is doing more work than any probability on the page. Treat the 3-day claim, then, as what it honestly is, an empirical countdown built on a small but genuinely suggestive sample, resting on real emergence physics, with error bars wide enough to drive a truck through. What makes the countdown compelling tonight is not its precision. It is that both of its possible endings are dramatic. If the pattern holds, then within the next day and a half you will watch the most dangerous object on the sun diffuse itself in real time, a live demonstration that these monsters follow a script, which would itself be one of the more useful things a solar observer could learn this year. If the pattern breaks, it breaks in the direction of a region that kept escalating past its deadline while aimed at Earth, with everything that implies about the ceiling on what it might yet do. And the needle is currently twitching toward the second ending. Remember the shape of the sequence. 4 eruptions on day 1, 1 on day 2, and then the strongest of the entire series on the morning of day 3. A textbook fade would have looked like day 2, tapering frequency, softening peaks. Day 3 was supposed to continue that slope downward. Instead, the region cleared its own bar. There are 2 readings of that, and they bracket everything. The generous reading. Even a settling region fires its largest stored release late, as the biggest accumulated strain finally lets go, a final chord, not a new movement. That would still fit the pattern loosely. Some of the recent dominant regions delivered their heaviest single blow near the end of their active phase before going still. The ominous reading. The escalation means emergence has not finished, that new flux is still rising into this region, still winding the springs, and the construction phase that was supposed to be ending is instead entering a second act. As of this morning's official analysis, the region was still described as growing and consolidating. Growth is not what a fading region does. Now put numbers on the window itself, because a countdown deserves arithmetic. Hold the official daily probabilities steady, 50% M-class, 10% X-class, and compound them across the roughly 3 days this region remains well positioned toward Earth. The chance of at least one more M-class flare over those days is about 87%, near certainty. More radio blackouts, more of exactly what brushed the Americas this morning. The chance of at least one X-class flare works out to roughly 27%, better than 1 in 4, and the highest sustained X-class exposure any Earth-facing region has carried this summer. And a subtlety worth absorbing. Those official percentages are recalculated from the region's classification each day. If the region's escalation forces tomorrow's classification upward, the compounding starts again from a worse baseline. The countdown does not just run, it can steepen while it runs. It is fair to ask where a number like 87% comes from, so let me show the arithmetic in one breath. The beauty of it is that you can check it on a napkin. If each day carries a 50% chance of at least one M flare, then each day also carries a 50% chance of none. For 3 independent days to all come up empty, those misses have to stack. 1/2 times 1/2 times 1/2, 1/8. 12.5% that nothing happens, 87.5% that something does. Run the same stacking on the X-class number. A 90% daily chance of no X-flare, 3 days running, is roughly 73%, leaving about a 27% chance that at least one X-class eruption fires before the geometry lets us off the hook. No secret models, no insider data, just the official published odds, honestly compounded. And notice the asymmetry in what those 2 numbers mean for the next 36 hours. More M-flares are close to guaranteed, so the drumbeat and the blackouts continue almost regardless of which ending the region has chosen. The M-flares are the noise of the window. Only the X, or the fade, is its answer. 1 in 4 from point-blank range, inside a day and a half. Those are the stakes as best they can honestly be stated. But a probability is not a mechanism, and there is an obvious question hiding under all of this that deserves its own answer. Why is the best science on Earth reduced to coin-flip language about a ball of plasma we have watched continuously from multiple spacecraft for decades? Why can nobody simply look at those delta cores and tell you whether the world fails tomorrow? The answer is one of the most humbling stories in modern physics, and it is the reason the word forecast, when applied to the sun, means something closer to actuarial table than prophecy. Part 5. Why no one can tell you what happens next. There is a machine 93 million miles away that we have photographed every few seconds around the clock for the better part of 2 decades. We can measure its surface magnetic field pixel by pixel. We can watch sound waves ripple through its interior and reconstruct, roughly, what lies beneath the visible surface. We have satellites staring at it in a dozen wavelengths without ever blinking. And with all of that, when the question is whether a specific sunspot region will produce a major flare tomorrow, the best answer human civilization can produce is 10%. Sit with how strange that is. We can predict the path of a hurricane days out. We can tell you when an asteroid will pass Earth in 20 years, to the minute. But the sun's eruptions, the events at the top of this region's menu, the ones that would matter most, remain fundamentally probabilistic. Not because the scientists are lazy or the instruments are weak, but because of what a flare actually is and where its trigger hides. A flare is not an explosion in the chemical sense. Nothing burns. A flare is a magnetic short circuit. In the corona above a sunspot region, magnetic field lines carry enormous stress, twisted, sheared, and pressed against each other by the churning of the surface below. Plasma physics allows those crossed field lines to suddenly reconnect, to snap into a new, lower energy configuration, converting the stored magnetic strain into heat, light, and accelerated particles within minutes. The energy release is astonishing. A single large flare can exceed the yield of billions of nuclear warheads, but the trigger is a threshold phenomenon. The field holds and holds and holds, and then a critical point somewhere in that invisible architecture tips, and it goes. Like an earthquake fault, like an avalanche slope, like a bent steel bar that takes strain silently right up until the instant it does not. And here is the cruel part. The threshold lives in the corona's fine structure, in the precise three-dimensional weave of field lines above the region, and that weave cannot be directly measured. Our magnetic maps read the field at the visible surface, one layer of a structure that extends thousands of miles upward. Everything above that layer is reconstruction, models extrapolating from the boundary. It is like trying to predict which tree branch will crack in a storm when you can only see the roots. Forecasters know the region carries the strain. They can see the delta cores grinding at the surface. What they cannot see is exactly how close any given weld inside that invisible weave is to its breaking point. So they do the only rigorous thing available. They classify the region by its visible architecture, look up how often regions of that class have flared historically, and publish the frequency. 50% M, 10% X. Those numbers are not a physical simulation of this region's future. They are an actuarial table, the sun's insurance rates, and region 4493 is currently paying the premiums of a very bad driver. The scale of the energies involved deserves one concrete anchor, because it explains why the threshold matters so much. The magnetic energy stored above a large delta region can reach 10 to the 32nd power ergs, comparable, in more familiar units, to tens of billions of the largest thermonuclear devices ever built, banked in invisible field lines above an area a few times the size of Earth. When reconnection trips, only a fraction of that reservoir converts, and the conversion is indifferent to our categories. Some becomes the X-ray flash we grade with letters, some becomes accelerated particles, some becomes the bulk shove that can launch a mass ejection. The same reservoir, tapped slightly differently, yields an M flare or an X flare, which is precisely why no bright line in the observable surface data separates a region, about to do one from a region, about to do the other. The reservoir is measurable, roughly. The tap is not. This is also why the region keeps outrunning its own forecast, a phenomenon you have now seen twice in this story. The morning it was born, the odds gave a slight chance of M-class. The first M-class arrived within hours. The daily forecast updates on a human schedule. An analyst classifies the region. The numbers publish. The sun proceeds to do whatever it does. When a region evolves in hours, as this one did during its 18-hour construction sprint, the classification lags reality. The number 10% published this morning describes the region as it was mapped. It says nothing about the region as it will be by tonight, if the growth that analysts flagged this morning continues. Probability tables cannot chase a moving target. That gap between the map and the territory, hours wide at the worst possible time, is the honest uncertainty at the center of this window, and no agency on Earth can close it. Within all that machinery of doubt, there is one genuinely hopeful mechanism, and it deserves its moment. The cage we described earlier. The great overlying loops pinning this region's core have so far kept every eruption confined. Flash without shrapnel, flare without ejection. And confinement is not merely a lucky catch. Some physicists read a drumbeat of contained flares as a region gradually spending its budget, each M-class release converting stored strain into light and heat that escapes harmlessly, like a pressure valve hissing off steam a little at a time. Under that reading, 5 M-flares in 48 hours is the sound of the bomb diffusing itself, and the 3-day pattern is just the audible version of a region running out of money. It is a real mechanism, it has real support, and it may be exactly what is happening. But the literature carries the opposite reading too, and no honest video can leave it out. Confined flares can also be the overture. Each contained eruption rearranges the field around the core, and some of those rearrangements weaken the cage itself, eroding the overlying loops until the next release finds a way through. The record of September 2017 again looms. Contained activity, then transformation, then the giant eruptive flares. 2 interpretations, same data. Pressure valve or countdown. The instruments cannot distinguish them from here. Only the region's next move can. That is not a failure of nerve on the forecaster's part. It is the current edge of human knowledge about our own star, drawn in real time across the next 36 hours. And the field has tried to do better than the actuarial table. Understand that this is not a discipline at rest. For decades, researchers have hunted for a reliable precursor, a measurable quantity that reliably crosses a line before a major flare. Shear angles along the polarity boundaries, electric currents inferred from the twisting of surface fields, the rate of magnetic flux emergence, the helicity injected hour by hour. Each has been proposed, tested against archives of thousands of regions, and found to improve the odds at the margins without ever yielding a trigger warning. The machine learning era has thrown neural networks at the same archives with the same verdict. Modest gains over the classification tables, no breakthrough. There is even a sobering literature on how well the published probabilities themselves verify, and the record shows the system is honest, in some stretches slightly overcautious, with the rarest events historically arriving a touch less often than forecast. Take that in for what it genuinely is. The 10% is not a hedge or a guess. It is the distilled residue of every method humanity has tested, all of them converging on the admission that the corona keeps its final secret until it spends it. I want to pause on something before we move to the geometry, because it colours everything about how you should hear those probabilities. This is the part of the cycle when the sun is supposed to be winding down. The smoothed sunspot number for June was 94, down more than 20 points from a year ago. The cycle's peak is behind us. The long slide toward minimum is underway. By the simple bookkeeping of spot counts, this should be the boring stretch. And yet the last 4 weeks alone have delivered an X1.1, an X1.3, and now a third dominant Delta-class region in a row, each one assembling fast, striking hard, and handing the baton to the next. Fewer spots, but the ones that do form keep coming up complex, concentrated, and mean. The declining phase of a solar cycle has a long historical reputation for exactly this behaviour. Some of the most violent events of past cycles arrived years after their peaks. And last month, in our video on what scientists found changing beneath the sun's surface, we explored one speculative reason why: evidence that this cycle's magnetic activity has concentrated into a shallow layer near the surface, where the standard spot count bookkeeping underestimates it. Whatever the deep cause, the operational fact stands. The calendar says the sun should be relaxing, and the sun keeps manufacturing regions like this one. The era we're actually living in is meaner than the one the schedule promised. So this is the machine, honestly described. A 2-day-old giant, magnetically deformed in a way observers struggle to recall seeing, carrying multiple welded pressure points and probable X-class energy behind a cage of uncertain strength, escalating through the window in which its recent predecessors died down, in a phase of the solar cycle that keeps over-delivering, watched by a forecasting system that can quote you its rap sheet but not its next move. 10% per day, 1 in 4 across the window, which leaves the question that converts all of this from astronomy into something more personal. Suppose the 10% hits. Suppose the cage fails and this region fires the big one inside the window. Why would that matter more from this region, this week, than from any of the other giants this cycle has produced? The answer is nothing but geometry, the coldest, simplest fact in this entire story, and it is the reason this particular window has forecasters watching through their fingers. Part 6. The geometry that makes this matter. Location, on the Sun as on Earth, is everything. 2 sunspot regions can be identical in size, identical in complexity, identical in the violence of their eruptions, and one of them is a spectacle while the other is a threat, purely because of where they sit on the disk when they fire. To understand why this region's address has forecasters more attentive than its anatomy alone would justify, you need one picture in your head. The Sun rotates, and everything on its surface is on a slow conveyor belt moving from the eastern edge of the disk we see, across the centre, to the western edge, at about 13.2 degrees of longitude per day. A full crossing takes about 2 weeks. Where a region sits on that conveyor determines not whether its eruptions are powerful, but whether they are pointed at us. Flares and coronal mass ejections care about geometry differently, and the difference matters here. A flare is a flash of radiation. It travels in straight lines in all directions, so any flare on the visible disk touches our ionosphere regardless of position. The effect just weakens toward the edges as the flash comes in at a slant. That is why this morning's blackout happened even though nothing physical was thrown at us. But a coronal mass ejection, the billion-ton plasma projectile, the payload that drives the great geomagnetic storms, is a directed object. It launches outward from its source region, roughly along the direction that region faces. A CME from a spot near the sun's eastern or western edge goes sideways, a miss or a graze. A CME from a region near the center of the disk comes at Earth like a thrown ball at a catcher's mitt. Solar physicists even have a name for the signature, a halo event. Because when a CME comes straight toward you, coronagraph images show it expanding evenly around the sun in all directions at once, a ring of light swelling toward the camera. A halo is the sun's way of saying, "This one is yours. Now place our region on the conveyor." It was born at roughly 13 degrees east of the central meridian, just left of dead center. Today, 2 days later, it sits at 20 degrees west, just right of dead center, having crossed the midline of the Earth-facing disk during the very stretch when its flares escalated. It could hardly be better aimed if it had been placed deliberately, and run the conveyor forward. At 13.2 degrees per day, the region reaches roughly 33 west by tomorrow, 46 west the day after, 60 west around July 25th. The traditional rule of thumb puts the strongly geo-effective zone, the range from which a CME has a solid chance of a direct or near-direct hit, from about 60 east to 60 west. Our region exits that zone around July 25th or 26th. After that, its eruptions progressively lose their grip on us. By month's end, it will be firing into empty space beyond the western limb, someone else's problem, or no one's. Notice what those two clocks just did. The pattern clock says the region's fury resolves within 36 hours. The geometry clock says the region stays aimed at Earth for roughly 3 more days. The dangerous overlap, escalating region, point-blank alignment, is the window where those clocks intersect. Now. If the pattern holds and the region quiets by tomorrow night, it will have spent its entire violent life pointed at us, and never once let a projectile loose. If the pattern breaks and the region keeps erupting into next week, geometry gradually diffuses what the pattern could not. Every day of delay rotates the barrel a little further off target. The genuinely bad scenario is the narrow one in between, a cage failure in the next 2 to 3 days, while the region still faces us. That scenario is the 10%. That is the coincidence of clocks this whole vigil is about. The westward drift carries one additional physical meaning beyond CME aim, and it cuts the other way, worth 30 seconds because it is the one respect in which this region grows more connected to Earth as it rotates away. The solar wind does not leave the sun in straight lines. Because the sun rotates, the magnetic field lines it drags outward wind into a spiral, like water from a spinning sprinkler. From Earth's position, the field lines we are magnetically plugged into trace back not to the center of the disk, but to a region west of center. A sunspot group near 20 to 60 degrees west sits close to that magical foot point, meaning any energetic particles its flares accelerate get injected nearly straight down the magnetic highway to us, arriving in tens of minutes rather than diffusing for hours. Solar physicists call such regions well connected, and it is the reason the radiation storm gauge from Part 3 stays interesting, even as the CME geometry slowly improves for us. Over the coming days, this region's flares lose their aim at Earth with plasma, while gaining their aim at Earth with particles. There is no week in a disk crossing when a region like this is entirely safe from every angle. There are only different flavors of exposure. It is worth being concrete about what a direct hit from a large, Earth-directed CME actually does. Briefly, this channel has covered the full anatomy of severe geomagnetic storms in other videos, including our look earlier this month at the power grid's fragile summer. So consider this the short version, with the details left on the shelf. The projectile takes 1 to 3 days to cross the gap, depending on speed. Arriving, it drapes Earth's magnetic field in its own, and if the fields align the wrong way, they merge, pouring energy into the magnetosphere, driving electrical currents in the upper atmosphere that mirror themselves into the ground beneath, into pipelines, rail networks, and the long transmission lines of power grids. Satellites feel increased drag and charging. Navigation signals degrade, aurora surges toward latitudes that see it once a decade. The scale runs from G1, the minor storm forecast for tonight, to G5, a designation Earth has experienced only a handful of times in the space age, most recently in May of 2024. Whether a given CME lands as a nuisance or a news event depends on its speed, its mass, and above all the orientation of its internal magnetic field. One more thing no one can measure until the projectile is nearly here. The point for tonight is simpler. None of that machinery engages at all unless the geometry lines up. This week, it lines up. Speed, for the record, is what separates the nuisance arrivals from the historic ones, and the range is wider than most people imagine. A pokey coronal mass ejection ambles across the Sun-Earth gap at 400 km per second and takes more than 3 days to arrive, weakening as the wind ahead drags on it. The great ones leave the Sun at 2,000 or 3,000 km per second, and the very fastest in the historical record made the crossing in well under a day. Each factor of speed compounds at arrival. A faster projectile carries more momentum into the magnetosphere, drives its shockwave harder, and compresses the timeline between detection and impact, shrinking the world's window to prepare from days to hours. When forecasters model an eruption, the launch speed read from coronagraph frames is the first number they reach for, and the arrival estimate it feeds is typically good to within about 10 hours in quiet conditions. Hold that phrase, in quiet conditions, because the wind between here and the Sun is about to stop being quiet, and that caveat is where the next chapter lives. There is a quieter thread woven into the geometry story that regular viewers have earned, and it takes one sentence. As we covered last week in our video on the weakening of Earth's magnetic shield, the field that has to catch whatever comes is itself measurably softer than it was a century ago. The receiving surface is not what it used to be, which is one more reason alignment weeks reward attention. One sentence as promised. The full story lives in that video. Before we leave the geometry, one loose end from earlier needs pinning to the map, because it acquired new meaning the moment you learned where this region sits. That faint ejection from yesterday, the filament that erupted at 10:45 Universal Time just northwest of the region, and the dim puff the coronagraphs caught leaving the northwest limb a few hours later. Northwest of a region at disk center is not deep space. It is the neighborhood just off our line of sight. The official modeling, as of the latest discussion, had not yet determined whether that ejection carries any Earth-directed component. The language remains carefully conditional, and faint means faint. Even a grazing arrival would likely register as nothing more than a flutter in the solar wind late on July 24th or so. But it is the first object in this story to leave the Sun on a trajectory that even might include us, and its answer is still pending. Keep it on the board, and now the board is nearly full. A loaded region at point-blank alignment, its clock running. A pending verdict on a faint first projectile. What remains is the piece arriving tonight, the one element of this story with a confirmed delivery time, because while all of this magnetic drama unfolds at the center of the disk, the wind from that 400,000-mile hole we covered 4 days ago has spent those 4 days crossing 93 million miles of space, and its leading edge reaches this planet within hours. On any ordinary week, a minor stream storm is background texture. This week it changes the physics of everything else on the board. Because if the region does fire while the stream is flowing, the two events do not simply happen side by side, they interact. And the history of what happens when eruptions travel through disturbed solar wind is strange enough to deserve its own chapter. Part 7. The wind arrives tonight. While one part of the Sun spent this week building a monster, another part has been missing entirely. 4 days ago we walked through it in full, a coronal hole, a region of the Sun's outer atmosphere where the magnetic field, instead of looping back down to the surface, opens straight out into space like a door left ajar. Through that open door, the solar wind escapes at nearly double its usual speed. The hole we covered on July 18th was a giant, a dark trans-equatorial gash stretching some 400,000 miles, and at that time it sat facing Earth, which meant its accelerated wind was aimed at us. Solar wind is not instantaneous. The stream takes days to cross the gap. The forecast then was arrival around July 20th to 22nd, with a minor storm likely. Tonight that forecast comes due. The numbers as of this afternoon read like the held breath before it. Solar wind at Earth flowing at 423 kilometers per second. Ordinary. The interplanetary magnetic field at a mild 4 nanotesla, tilted only slightly southward. The planetary disturbance index topping out at 3 over the past day, below storm level everywhere. Aurora activity. Quiet. And against all of that stillness, the official 3-day forecast draws a sharp line through this very evening. Between 2100 Universal Time and midnight, the planetary index is expected to hit 5, the threshold of a G1 geomagnetic storm, as wind speeds climb towards 600 to 700 kilometers per second. The rationale line in the forecast is as dry as these things get. G1 storming likely due to negative polarity coronal hole high-speed stream effects. The wind from the hole you already know, arriving on schedule tonight. There is even a signature in the data showing the stream announcing itself. Yesterday afternoon, hours before any storm, the interplanetary magnetic field at Earth abruptly stiffened. Total field strength jumping to 17 nanoteslae for a stretch, more than 4 times today's ambient reading, before relaxing again. That spike is characteristic of the structure that leads every high-speed stream, the compression region, where fast wind piles into the slower wind ahead of it, like a fast car tailgating traffic. The plasma and magnetic field caught in that pile-up get squeezed, density up, field strength up, and that compressed wall, arriving before the fast stream itself, often does the initial damage to Earth's magnetic calm. The corrugation between slow and fast wind even has its own name in the trade. A co-rotating interaction region, the spiral wall of compression that sweeps past Earth like the arm of a slow lawn sprinkler, once per solar rotation, for as long as the hole survives. Feel free to forget the terminology. Keep the picture, wall first, river behind. The forecast table for the next 3 days is worth reading aloud, because its shape tells the story of a passing stream with a single night of teeth. Tonight, July 22nd, the peak. Planetary Index 5, minor storm, in the 2100 to midnight window. Tomorrow, July 23rd, a maximum of 4, elevated, unsettled, below storm level, as Earth rides deeper into the stream's body, where the wind stays fast but the compressed leading wall is passed. July 24th, 3.67, easing further as the stream begins to rotate off. 1 night of storming, 2 days of afterglow, and beneath the table sits the recurrence everyone who covered the hole 4 days ago already knows. Coronal holes are the Sun's most durable structures, routinely surviving multiple rotations. If this one persists at its current scale, and it was still growing when it faced us, the same stream sweeps past Earth again roughly 27 days from now, in mid-August, and possibly again in September. Tonight is not a one-time event. It is the first scheduled visit of a returning tenant. What does tonight's G1 actually mean, on the honest scale? Modest things, mostly beautiful ones. A G1 storm means the aurora expands its territory. Instead of hugging the Arctic, the oval pushes toward the northern tier of the United States, the Dakotas, Minnesota, Montana, Maine, and southern Canada, and mirror image latitudes south. It can mean weak fluctuations on power grids at high latitudes, the kind engineers note in logs and correct without drama. Satellite operators watch drag estimates a little more closely. Nobody's lights flicker. There is a seasonal catch for sky watchers, one we flagged 4 days ago. Late July nights at those latitudes barely get dark. Astronomical twilight lingers, and a modest aurora can be washed out by the sky itself. If you are far enough north with a clear northern horizon after local midnight tonight, it is worth stepping outside. Just know the sun's own leftover daylight is working against you, and there is one number in tonight's data that deserves more respect than its obscurity suggests. The storm's forecast peak is KP5, and the strength of the response will hinge on a quantity called BZ, the north-south tilt of the magnetic field embedded in the arriving wind. Earth's magnetic field points north. If the field wrapped in the stream tilts south when it arrives, the two fields connect and energy flows in. The storm delivers. If it arrives tilted north, the door stays shut and the same wind slides past with barely a ripple. Right now, BZ hovers at -3 nanotesla, slightly south, mildly favourable for storming. But that number swings hour to hour and cannot be predicted in advance, only measured as the wind sweeps over our upstream monitoring spacecraft, parked 1 million miles sunward. Those sentinels give us 15 to 60 minutes of warning of what the next parcel of wind carries. For a minor stream storm, that is trivia. File it anyway, because the same 1-hour blind spot applies to every arrival from the sun, including the kind this window is really about, and it is one of the sharpest limits on the entire warning system standing between the sun and your infrastructure. A word on the machines that will call the arrival in real time, because they are the unsung heroes of every storm night. 1 million miles sunward of Earth, at the gravitational balance point where a spacecraft can hover indefinitely between the sun's pool and ours, sit our upstream sentinels, the solar wind monitors whose entire job is to be hit first. Tonight, when the stream's leading wall sweeps across them, their instruments will read the jump in speed, density and field within seconds, and the numbers will appear on public dashboards around the world before the wind itself has covered the final 1 million miles to Earth. That is where the 15 to 60 minute warning comes from. It is simply the travel time from the sentinel to us, longer when the wind is slow, shorter when it is fast. Watch those feeds tonight around 2100 Universal Time, and you will see the storm arrive twice, once at the spacecraft in the data, and once at Earth, in the magnetometers, most of an hour later. It is the closest thing space weather has to hearing thunder after seeing the flash. 2 more instrument readings complete tonight's picture, both quietly connected to the whole. First, Earth's outer radiation belt is running hot, and has been for days. The flux of high-energy electrons at geostationary orbit, the altitude where weather and communication satellites live, has been above the alert threshold of 1,000 particle flux units continuously since July 17th, peaking at 1,039 on July 20th. That is 5 straight days of the alert condition that satellite engineers associate with a slow hazard called deep dielectric charging. Energetic electrons burying themselves in spacecraft insulation, accumulating charge that can eventually arc and glitch electronics. This elevated flux is largely a legacy of the fast wind era we have been living through. Streams like tonight's pump the belts full of accelerated electrons, and tonight's arrival will likely keep the streak alive into a 6th day and beyond. No spacecraft is in acute danger, but it is one more line on the picture of a near-Earth environment that has not been allowed to rest all week, even before the region at disk center does anything at all. Second, and pure atmosphere. For the first stretch of hours after the stream arrives, 2 solar structures will be touching Earth at once, the hole's wind streaming past while the sunspot's flare radiation intermittently pulses the day side. 2 entirely different mechanisms, from 2 entirely different solar features, sharing this one small planet on the same July night. The sun does not coordinate its weapons, it does not need to, which brings us to the question this part exists to set up. Tonight's storm, alone, is a G1, a whisper. The region at disk center, alone, is a flare machine that has so far thrown no mass at us. But the window we're inside is defined by the possibility that the second thing changes, that the cage fails and an eruption launches while the stream is still flowing past Earth. And when a coronal mass ejection is fired into solar wind that is already fast, already structured, already turbulent, something happens that forecasters genuinely dread, not because it makes the impact automatically worse, but because it makes the impact fundamentally harder to predict. The gap between the sun and Earth stops being empty road and becomes traffic, and traffic on this highway has produced some of the strangest events in the history of space weather, including a storm that once made the ocean itself explode. Part 8. Traffic on the highway to Earth. Space, we are taught, is empty. For the purposes of this story, forget that. The 93 million miles between the sun and Earth are a flowing medium, a river of solar wind, denser here, faster there, threaded everywhere with magnetic field. Everything the sun throws at us has to travel through that river, and the state of the river when the projectile enters it shapes what arrives at the far end, how fast and how hard. Tonight the river runs fast and rough. That is the fact that makes this week's overlap more than a scheduling curiosity. Start with what a high-speed stream does to a coronal mass ejection launched into it, because the interactions run in both directions. The stream can be shield, and it can be accelerant depending on timing and position. The shield case, a CME that plows into the compressed wall at a stream's leading edge is punching into denser magnetically stiffened plasma. The impact can slow it, distort its shape, even shove it partly off course. Deflections of these kinds have been tracked repeatedly in multi-spacecraft observations. When this region was born 2 days ago, analysts made exactly this point about its position. The adjacent stream means any eruption it fires toward us has to fight through that structure on the way. A modest CME, arriving off angle, might be blunted into insignificance by the traffic. The accelerant case is the one that keeps forecasters up at night. A CME travelling within or just behind fast wind is moving through thinner, faster-moving material. Less drag, less deceleration. Ordinarily, the river slows large eruptions substantially during the crossing. A projectile-riding prepared road keeps far more of its launch speed all the way here. Same eruption, same sun. Arrival conditions can differ by a day of travel time and a full storm class, purely based on the traffic pattern it entered. That is why forecasters treat eruptions during stream passages as their least favourite forecasting problem. Every input in their arrival models becomes a moving target. The most extreme demonstration of the accelerant case in the space age is worth 30 seconds of your time because it is barely believable. In early August of 1972, an enormous sunspot region fired a sequence of major eruptions over several days. The early ones swept the highway clean, clearing the slow, dense wind out of the corridor between the Sun and Earth. Then came the final blast into a vacuum-swept lane. It crossed the entire Sun-Earth gap in about 14.6 hours. That remains, more than half a century later, the fastest recorded transit ever, a trip that typically takes 2 or 3 days done before the workday ended. The resulting storm compressed and convulsed Earth's magnetic field, violently enough that dozens of American naval mines in the waters off North Vietnam, mines designed to detonate when a passing ship's steel hull disturbed the local magnetic field, began exploding on their own in the space of minutes, with no ships anywhere near them. The United States Navy investigated and formally attributed the detonations to the solar storm. The Sun, from 93 million miles away, had triggered weapons of war in an ocean on Earth. Hold on to that image, the Sun reaching into human conflict, because the next act of this video is built entirely on it. The 1972 storm carries one more credential worth logging, beyond its speed record and its mines. It remains a benchmark for the radiation hazard side of the ledger. The proton storm it unleashed was among the most intense of the space age, and it happened to fall in the gap between 2 crewed moon missions. A coincidence studied intensely ever after, because the radiation environment it created beyond Earth's magnetic shelter would have posed a serious threat to astronauts caught in transit. One eruptive sequence, and it produced the fastest recorded transit, a major radiation storm, exploding naval mines, and a permanent entry in every spacecraft design manual. Sequences, again. The Sun's worst weeks are conversations, not statements. For this week, the 1972 lesson distills to one principle. Sequences are worse than singles. A lone eruption into quiet wind is a physics problem forecasters solve routinely, with arrival estimates good to better than half a day. Eruptions into structured, fast, or previously swept wind produce compounding uncertainty. Arrival times that can slip or leap by many hours, impact strengths that can multiply or evaporate. Our region has so far launched nothing, but it has fired 5 times in 48 hours. Its cage will not last forever if the escalation continues, and beginning tonight, for the next 2 days or so, its firing line runs directly through an active stream. Every ingredient of a forecasting nightmare short of the eruption itself is now on the table, inside the same 36 hours the pattern flagged in advance. There is also a subtler, gentler layering already in motion, one that requires no cage failure at all, only the pieces confirmed to be in flight. The stream governs Earth's magnetic weather tonight through tomorrow, tapering through July 24th as the fast wind gradually gives way. Simultaneously, 2 faint possibilities are drifting inbound. The ejections that left the Sun on July 20th, from other locations launched before our region even mattered, which models give a low-confidence chance of grazing Earth late on July 23rd, and yesterday's faint filament ejection, verdict still pending, which if Earth-directed at all would arrive in the same general stretch. None of these, alone, is stronger than a G1, but geomagnetic disturbances stack. A magnetosphere already rattled by stream wind responds more energetically to a fresh shove than a calm one does, which is precisely why the official forecast holds open a chance of renewed minor storming through July 24th rather than declaring the week over after tonight. Picture the next 72 hours as a sea already running a heavy chop, with 2 possible wakes crossing it, and 1 loaded cannon on the shore that has not yet decided whether to fire. Nothing in that picture is individually severe. All of it, together, is the roughest near-Earth stretch since this remarkable July began, before the main question is even answered. There is a special case of eruption into traffic that deserves its own name, because if this week goes wrong, you may hear forecasters use it: the cannibal event. When a region fires 2 coronal mass ejections in quick succession, hours to a day apart, and the second is faster, the second can overtake and consume the first mid-flight, the 2 merging into a single compound front that arrives carrying the mass of both and a magnetic structure more tangled than either. Compound arrivals of this kind have driven some of the sharpest storm intensifications on record, because the merged front can hold its punch together in a way single ejections often cannot. Note what the recipe requires: a single active region, still growing, firing repeatedly across a short window. A region, in other words, behaving exactly like the one at the center of this video should its cage ever fail twice. Let us also be scrupulously fair about the ceiling, because this channel promised not to inflate tonight. If the region never launches, this entire chapter resolves as a minor storm tonight, some high-latitude aurora hunting hampered by summer twilight, possible flickers of renewed G1 late in the week, a radiation belt streak extending a few more days, and a forecasting community that exhaled. That is the most likely single outcome, and it would be a perfectly good week of space weather in its own right. The reason this chapter earned its place in the video is conditional, and the condition is the 10%. If the big release comes, the traffic conditions between here and the sun mean that everything about its arrival, the when, the how hard, even the weather, inherits the uncertainty of the river it must cross. The window does not just hold a possible eruption, it holds a possible eruption into the worst forecasting conditions of the month, and with that, the board for the next 36 hours is fully set. You know the machine, a 2-day-old giant with multiple welded cores and probable X-class energy behind a straining cage. You know the clock, day 3 of a 3-day pattern, already violated in the wrong direction. You know the geometry, point blank for 3 more days. You know the river, fast, rough, and about to get rougher tonight. Every element of this story so far has been about what we can see coming. The towers of data, the forecasts, the upstream sentinels, the probabilities updated daily and published for anyone to read. It is easy to take all of that for granted, to assume humanity always had this dashboard, always knew when the sun was shouting on our frequencies. We did not. And the single most important lesson about what happens without that dashboard was delivered on a spring morning in 1967, when the radio blackout, the same phenomenon that brushed your continent this morning scaled up 1,000-fold, fell across the one set of antennas on Earth that was listening for the end of the world. Part 9, May, 1967. The world you're about to step into ran on a hair trigger. In the spring of 1967, the United States and the Soviet Union sat aimed at each other with tens of thousands of nuclear weapons between them. The Cuban Missile Crisis was 5 years in the past, close enough that every officer on duty remembered exactly how near the edge had come. American nuclear-armed bombers flew continuous airborne alert patrols, engines running, weapons aboard, crews waiting for a coded order most of them prayed would never come. Doctrine on both sides rested on a single organizing principle. Whoever detected the other's attack first would have minutes, not hours, minutes, to decide the fate of civilization. Everything, absolutely everything, depended on detection. To feel the texture of that spring, put yourself in the operational world of May 1967. The bombers flying those alert patrols were part of a program that kept a portion of the strategic force airborne at all times, en routes arcing toward the Arctic. The shortest path between the superpowers runs over the pole, which is why everything in this story happens in the far north. In the Mediterranean and the Middle East, tensions were building toward the war that would erupt in the first week of June. Vietnam was burning through its bloodiest year yet. Command centers on both sides ran drills in which the time, from first radar detection to a launch decision, was measured against a stopwatch. It was, in short, precisely the kind of season in which ambiguity was least affordable, and the sun was about to deliver the most ambiguous signal imaginable into the most sensitive system on Earth. Detection had a name, and it had 3 addresses. The Ballistic Missile Early Warning System, BMEWs, in the acronym heavy language of the era, was a chain of enormous radar installations strung across the top of the world. Clear, Alaska. Thule, on the icebound northwest coast of Greenland. Fylingdales, on the moors of northern England. Each station stared over the polar horizon toward the Soviet Union, along the paths its missiles would fly, scanning for the first glint of launch. These radars were the tripwire of the nuclear age. If Soviet missiles ever rose, BMEWs would see them first and by the 15-odd minutes on which every retaliation plan depended. And precisely because they were the tripwire, military logic drew a hard conclusion about them, one worth reading twice. Any deliberate interference with these radars, any jamming, would be interpreted as an act of war, not a prelude to war, an act of it. Because the only rational reason to blind the tripwire was that an attack was already on its way. Now bring the sun onto this stage. On May 18th, 1967, astronomers watching the solar disk saw an unusually large sunspot group rotating into view, a sprawling complex of spots with intense, tangled magnetic fields, catalogued in the records of the era as McMath region 8818. It was, in the vocabulary this video has spent an hour building, the dominant region of its moment, enormous, magnetically complex and growing as it turned toward Earth. The men who tracked it did not have our vocabulary, the modern delta classification, the flare probability tables, the space-based X-ray monitors all lay in the future. What they had were sketches, magnetograms, and a handful of pioneering solar observatories run by the Air Force's fledgling weather arm. Because the American military, a few years earlier, had begun quietly building something almost no one had heard of, a solar forecasting service. A small corps of officers whose job was to watch the sun the way other forecasters watched clouds. Keep those men in mind. In 4 days they will matter more than any general on the planet. On May 23, 1967, the region let go. The flare it produced was so large it was visible to the naked eye in ordinary white light, a distinction so rare it defines the elite tier of historical solar events. The flash that gave the Carrington event its fame in 1859 was seen the same way, but the visible light was almost incidental. What made this eruption historic was its voice. The flare produced one of the largest solar radio bursts of the 20th century, a roar of radio noise across an enormous span of frequencies, from below 10 MHz up through 9 GHz, drowning the bands that human technology had only recently moved into. At 606 MHz, instruments recorded the burst peaking around 373,000 solar flux units. Compare, one more time, to this morning. The burst from our region measured 200 units and lasted 2 minutes. The 1967 event outshouted it by a factor of more than 1,000, and the sun's 10.7 centimetre reference flux, the standard gauge of the star's radio brightness, which sits near 149 today, briefly read on the order of 8,000. Pause on the naked eye detail, because it places this event in the rarest company the sun keeps. The visible surface of the sun is so blindingly bright that almost nothing that happens on it can outshine its own background. For a flare to be seen in white light, as a distinct brightening against the solar disk, by an observer with no special instrument beyond a safe filter, the energy release must be near the theoretical ceiling of what a sunspot region can produce. The confirmed historical list of such events is short enough to memorize its famous members, and the first entry defines the genre, September 1st, 1859, when Richard Carrington sketched a sudden white brilliance over a spot group and inadvertently time-stamped the greatest geomagnetic storm in recorded history, the one that set telegraph papers smouldering 17 hours later. May 23rd, 1967 belongs on that same shelf, whatever number a modern X-ray monitor would have assigned it. The X-scale itself would not exist for years. The white flash announced an event in the historic class. The men watching it knew, in real time, that they were seeing something from the record books. What they could not yet know was where its radio screen was about to land. Radio energy of that magnitude does not respect the boundary between astronomy and infrastructure. The burst poured over the sunlit hemisphere of Earth, and within it, over 3 particular installations that shared an unfortunate distinction. Clear, Thule, and Fylingdales all sat in daylight, and all three, by the geometry of that hour, were pointed across the polar sky in a direction that put the low-hanging sun within their field of sensitivity. The most sensitive radar receivers on Earth, built to detect faint echoes from warheads 3,000 miles away, suddenly found themselves staring into a star that had turned itself into the most powerful jammer in the solar system. All three stations degraded at once. Displays that should have shown clean, empty polar sky filled with noise, interference consistent to the operators watching, with deliberate enemy jamming, and the logic of the tripwire engaged exactly as designed. One station failing might be a malfunction. All three warning radars blinded simultaneously on independent hardware separated by thousands of miles. To the men in the command centres, that pattern had one plausible author, and it was not the sky. The conclusion followed the doctrine. The early warning system was under attack, and an attack on the early warning system meant the real attack was likely minutes behind. What happened next unfolded with the terrible smoothness of a machine doing what it was built to do. Within the North American command structure, forces stepped up their readiness. Additional nuclear-armed bombers, beyond the ones perpetually airborne, were brought toward launch status, crews moving toward aircraft that carried city-ending weapons, while commanders weighed options on the assumption that the continent might already be under attack. Every minute that passed with the radars still screaming static was a minute the decision tree branched toward its darkest limbs, and it is essential to understand from inside that room that nobody was being irrational. Given what they knew, radars jammed, tensions high, doctrine clear, escalation was the correct procedure. The system was functioning perfectly. It was simply functioning on a false premise, because the one fact that mattered had not yet entered the room. The jammer was 93 million miles away, and it had no intentions at all. The world in that hour needed someone standing in the gap between those two versions of reality. Someone who could look at the same screaming radars and recognize not an enemy, but a star. And the extraordinary thing, the thing that makes this story worth telling 59 years later on a night when another giant region ticks through its window, is that such people existed. Barely. A handful of them, in a brand new discipline, holding information that had never before in history been operationally urgent. What they did in the next minutes is the entire reason this story has a next chapter, and the reason you have likely never heard of it is that the catastrophe they prevented never got to happen. Part 10. The Forecast That Stopped a War. Inside the mountain at Cheyenne, in the command post of the North American Air Defense Command, the question finally travelled down an unlikely corridor. Amid the escalating readiness, someone in the command structure asked the weather desk a question that, on almost any other day in military history, would have been trivial. Is anything happening on the sun? The question landed with the Solar Forecast Center, the small solar watching unit the Air Force had stood up within its weather service only a few years earlier. The forecaster on duty that day was a young officer named Arnold Snyder, and decades later, when researchers reconstructed the event for the scientific record, retired Colonel Arnold L. Snyder described the moment plainly. The command post wanted to know about solar activity, and he had an answer ready, because his unit had been watching the great region for days, had seen the morning's eruption develop, and knew the sun was in the middle of one of the most violent radio outbursts ever observed. Yes, something was happening on the sun. The largest thing his discipline had ever measured, in fact, and it was happening in exactly the frequency ranges the radars used. Then came the piece of reasoning that deserves to be taught in every course on scientific thinking, because it converted an observation into salvation. The forecasters and the radar operators together checked the geometry. All three affected stations, Alaska, Greenland, England, were in daylight, and all three were pointed across polar sky that put the sun near their line of sight. A Soviet jamming operation would have no reason to track the position of the sun. Solar radio noise could do nothing else. The pattern that had read as coordinated enemy attack, 3 independent radars failing simultaneously, was recast in a single stroke as the signature of a single natural source, shouting over all of them at once from above the horizon. Same data, opposite meaning. The difference was one team of people who knew the sun could do this. Consider how thin the thread actually was. The Air Force's solar forecasting network in 1967 was years old, not decades. A handful of observatories, a small rotation of trained officers, a discipline so new that its practitioners were still inventing its vocabulary. The unit existed at all only because a few far-sighted planners had argued, against considerable indifference, that the sun might someday matter operationally. On May 23rd, the entire return on that investment came due in a single conversation. Had the forecast centre not been staffed that morning, had the region not been tracked for the preceding days, had the command post simply not thought to ask the weather desk, any one broken link and the men holding the tripwire would have been left with only the enemy hypothesis and a clock. History's judgment on close calls tends to flatten them into inevitabilities, as if the system was always going to catch the error. Stand inside the minutes, and nothing about it was inevitable. It was a race between an explanation and a doctrine, and the explanation won by a nose. The information moved up the chain, and the escalation stopped. The additional bombers stood down, the aircraft stayed on the ground. The decision tree pruned itself back from its darkest branches. In the reconstruction published decades later, the definitive account, assembled by space physicist Dolores Knipp and colleagues in the journal Space Weather in 2016, drawing on declassified records and the recollections of the men who were there, the judgment of historians and participants alike is stark. Solar forecasting information, delivered in those minutes, is likely what prevented the situation from tipping into military action. The study's larger framing has become quietly famous in the field. This was extreme space weather met by extraordinary responses, and the response that mattered most was somebody in the right room understanding the star. The sun, incidentally, was not finished. The flare was only the opening act. Behind the radiation came the slower punch, the ejected mass, ploughing toward Earth over the following days, and when it arrived it ignited one of the great geomagnetic storms of the 20th century. The aurora, normally caged in the Arctic, surged south until it stood visible in the skies of New Mexico. Radio communications across the sunlit and nighttime Earth alike were disrupted on and off for the better part of a week, the United States military's own long-range communications among them, degraded this time not by the flare's radio scream, but by the wrecked state of the ionosphere itself. Had the storm's opening moments been misread, the days that followed would have offered no calm in which to discover the mistake. The system got one chance to be right, early, and took it. Here is the strangest coda to the story. For nearly half a century, almost nobody knew it had happened. The men involved went back to their duty rotations. The records sat classified or simply unexamined. The discipline the event created grew up largely ignorant of its own founding crisis. Only in 2016, 49 years later, did the full reconstruction reach the public, when Knipp's team gathered the surviving forecasters and radar officers, cross-checked their recollections against declassified documents, and published the account that finally put May 23, 1967, into the histories of both the Cold War and space physics. Snyder and his colleagues were, by then, retired colonels in their 70s and 80s, telling a story most of the world had never heard about the day their obscure specialty may have saved it. Think about what that gap means. The closest the sun has ever come to triggering a human war was invisible to the public for 2 generations, not because anyone was hiding a catastrophe, but because the system worked and averted disasters generate no headlines, no commissions, no anniversaries. The most consequential solar storm of the 20th century is the one you never learned about in school, precisely because the right people understood it within minutes. Remember that asymmetry the next time a quiet week of space weather tempts you to conclude the watching does not matter. The watching is why the weeks stay quiet. Now widen the lens, because the 1967 event did not just spare the world a war, it built the world you're watching this video from. Before May of 1967, solar forecasting was a scientific curiosity that the military funded modestly and consulted rarely. After it, space weather became a national security discipline permanently. The near-miss did for solar monitoring what only institutional terror can do for a budget line. The military's investment in observing, understanding, and predicting. The sun deepened and never again receded, threading forward through every subsequent decade, into the constellation of dedicated solar observatories, the upstream Sentinel spacecraft sampling the wind 1 million miles ahead of us, and the round-the-clock operational forecasting offices whose modern descendant is the Space Weather Prediction Center, the same institution whose bulletins this video has been quoting all night. Every probability table, every storm watch, Every forecast discussion passed in the first hour of this video flows by direct institutional lineage from the day the sun jammed the tripwire. And one more layer down, beneath even the Cold War, sits the discovery that started the whole discipline, worth a brief detour because it rhymes so perfectly. 25 years before the near war, in February of 1942, British radar stations tracking German aircraft found their screens suddenly flooded with fierce interference. The operator's first conclusion was the same one NORAD would reach a generation later. Enemy jamming, some new German countermeasure. The scientist tasked with investigating, a physicist named James Stanley Hay, traced the interference instead to an unexpected culprit, the Sun, then hosting a large sunspot group, radiating radio noise no theory of the day predicted. Hay had discovered solar radio emission itself, and the finding was promptly classified as a wartime secret. The Sun's radio voice was born into human knowledge as, quite literally, a suspected weapon, mistaken for enemy action at its very discovery, then mistaken for enemy action again in 1967, at the edge of a far greater war. Twice, in the span of one generation, humanity's first instinct on hearing the sun was to reach for the trigger. The entire discipline of space weather monitoring exists to make sure there is never a third time, which returns us, with new eyes, to a Tuesday morning in July of 2026, to a 2-minute, 200-unit radio burst from a 2-day-old sunspot region, and a minor blackout washing across the Americas while most of a continent slept through it. Nothing about this morning made news. No radar operator anywhere on Earth wondered, even for a moment, who was jamming them, because within minutes, anyone who cared could read exactly which region fired, exactly how strong the burst measured, exactly when the ionosphere would recover. The event was identical in kind to 1967, separated only by 3 orders of magnitude, and by 59 years of infrastructure built so that scale would be the only difference that mattered. This morning was the system working so well it was invisible. But invisible is not the same as finished. The region that fired this morning's burst is still there, still growing, still inside its window, and the system watching it, for all its modern reach, still cannot answer the only question that counts. Whether the window closes with a fade or a flash is a verdict the sun alone renders. So the last thing this video owes you is the honest shape of the next 36 hours, what the watchers will actually be looking at, what each outcome would look like from your side of the screen, and what this whole strange July teaches about the star we live beside. Part 11. What people are saying, and what the data actually shows. Whenever the sun does something dramatic, the internet does something predictable. This week has been no exception, and because this channel takes its viewers seriously, we are going to walk through the 3 claims spreading fastest right now, honestly, without a sneer, because each one contains a kernel worth examining before the science has its say. The first claim is the boldest, that the forecasters already know a monster flare is coming and are simply not telling you. Posts to this effect are circulating widely. Some flatly assert that we are due for a big solar flare within the day, that the quiet language of official bulletins is a managed front, that the real internal numbers are worse. The kernel of truth here is psychological, and it is real. Official space weather language is conservative. Agencies burned by decades of media hype write in probabilities and hedge words, and to a lay reader that restraint can smell like concealment. But the claim itself dissolves on contact with how this system actually works, and you have spent this entire video watching why. Every input the forecasters use is public. The X-ray flux from the monitoring satellite streams to the open internet in real time. You can watch this region's next flare land on a public chart within minutes of the light arriving. The magnetograms are public. The probability tables published daily, unredacted. The forecast discussions we quoted tonight are free documents anyone can read. There is no second, secret dashboard. The 10% X-class figure is the state of the art, and the honest chaos we walked through in Part 5, thresholds hidden in unmeasurable coronal structure, is precisely why nobody, at any clearance level, holds a better number, and the word due deserves its own burial. Flares are threshold events, not scheduled ones. The sun holds no queue. A region can carry X-class energy to the western limb and never spend it. Due is how gamblers talk about dice, and the dice do not remember. The second claim rises every time a big region crosses the disk, that solar activity triggers earthquakes, that the same week bringing M flares will bring seismic catastrophe, and the two are causally linked. This one has a longer pedigree and a more interesting kernel. The sun genuinely does drive electrical currents in Earth's crust during geomagnetic storms. That much is textbook. It is the same induction that threatens transformers, and researchers have periodically published statistical searches for a solar seismic correlation, a few claiming weak signals. We have covered those papers on this channel before, and our standing conclusion has not moved. The energy accounting fails by orders of magnitude. The currents a storm induces in the ground are vanishingly feeble compared to the tectonic stresses that load a fault. The comparison is a whisper against a mountain, and the statistical claims have not survived replication at meaningful magnitudes. Earthquakes this week will be earthquakes. The planet averages more than 100 of magnitude 4.5 or greater every week, storm or no storm, and the 7-day count in this morning's data, 152, sits squarely in that ordinary range. The sun jams radios. It does not throw faults. The third claim is the newest, and it aims at the heart of this video. That the 3-day pattern itself is a cover story, a narrative planted to explain away activity that is somehow engineered, or to prime the public before something bigger. The kernel here is the healthiest of the three. Skepticism about tidy patterns is exactly the right instinct, and this video has spent its full runtime applying that skepticism. You watched us stress test the pattern's sample size, name its counterexamples, and refuse to promote it from observation to law. But the answer to the conspiratorial version is beautifully simple. Every observation behind the pattern is reproducible from public archives. The flare records of the recent dominant regions sit in open databases. Anyone with a web browser can chart them and count the days of fury for themselves. A pattern you can independently verify from public data is the opposite of a cover story. The 3-day claim might well be wrong. That is a live possibility this video takes seriously. But if it fails, it will fail in public, on charts anyone can draw, possibly within the next 36 hours. Concealment does not schedule its own falsification test. For anyone who wants to do the verification rather than take my word for it, the trail is short and genuinely satisfying. The X-ray flux that grades every flare streams from the weather satellites to a public plot you can find in seconds. This morning's M3.6 is sitting on it right now, a sharp spike at 6:35 Universal Time, and the next eruption will draw itself there live. The daily forecast discussions, the documents with the growth and consolidation language and the delta configurations, publish every morning as plain text. The 3-day forecast table with tonight's storm window, the region-by-region classifications, the historical flare archives going back decades, all indexed, all free. This channel's role is synthesis and story, never access. There is no number in this video. You cannot pull yourself from a public source tonight. That, incidentally, is the standing answer to every future claim of hidden solar knowledge you will ever encounter. The sun is the single most watched object in human history, monitored by the militaries, science agencies and amateurs of every technological nation at once, all publishing in parallel. It is the worst-kept secret in the solar system. Step back from the 3 claims and notice what they share. Each one, at its core, is a story about hidden knowledge. Someone knows the flare schedule, someone knows the earthquake link, someone planted the pattern, and the deepest rebuttal is the story you just heard from 1967. When the stakes were as high as stakes have ever been, when misreading the sun meant nuclear war, what saved the world was not hidden knowledge. It was open knowledge, held by a small team, shared up the chain at the moment it mattered. The entire architecture built since that day runs on publication. Public data feeds, public watches, public discussion products, precisely because the lesson of the near war was that secrecy about the sun kills. An infrastructure genetically descended from that lesson is a strange candidate for a conspiracy of silence. Since we are being practical, let us answer the question a reasonable viewer actually has tonight. Is there anything you should do about this window? For tonight's minor storm, nothing protective, one thing recreational. If you live in the northern tier of the United States, southern Canada, or equivalent latitudes, check the sky north of you after local midnight and manage expectations against the summer twilight. For the window's larger possibility, the honest answer is that a 10% daily X-class chance calls for exactly 0 changes to anyone's life. No supplies, no unplugging, no anxiety. What it rewards is attention, This is one of those rare stretches when the most dramatic physics in the solar system is scheduled, public, and watchable in real time. And knowing what the plots mean, as you now do, turns a probability table into a spectator sport. If the big one does fire, the systems designed for that contingency engage on their own timelines. Agencies notify grid operators directly, airlines reroute on their own criteria, satellite teams execute procedures written years in advance. None of it requires anything from you, and none of it is improved by worry. The most useful thing a viewer can bring to the next 36 hours is the thing this channel exists to provide: calibration. Know what is normal so you recognize what is not. There is one more perspective worth offering before the final part, a calibration for anyone this video has made anxious. Consider what this morning actually was, compared against what the same morning would have been in other eras. In 1859, a naked-eye flare announced itself with sparks from telegraph sets and fire-red skies, and nobody on Earth knew why. In 1942, the sun's radio shout was mistaken for a German weapon. In 1967, the same shout, louder, was mistaken for the opening move of Armageddon, and bombers rolled toward runways. In 2026, a region 1,000 times quieter than the 1967 monster fired at dawn, and the sum total of human consequence was some high-frequency radio dropouts, a few automated alerts, and forecasters adjusting a probability table before lunch. That is not luck. That is 59 years of compounding vigilance, doing silently what it was built to do. The reason a loaded gun at Disk Center reads tonight as a fascinating vigil, rather than an emergency, is that thousands of people and dozens of machines are doing the watching for you, in the open, on schedules, with their work posted publicly every day. Which is exactly why the honest uncertainty that remains deserves respect rather than fear. The system can see everything except the one thing that matters, the moment of decision inside the region itself. Tonight that decision belongs, as it always has, to the sun. So let us end where the story must end, inside the window, with the clock running, counting what the next 36 hours can actually bring. Part 12, 36 Hours. So here we stand at the edge of the window, and it is time to lay out the endings, because one of them is going to happen, and you deserve to know what each looks like from your side of the screen. Ending 1. The Fade. Sometime between tonight and tomorrow night, the drumbeat slows. The background X-ray simmer cools from its constant sea-level murmur back toward genuine quiet. Tomorrow's region analysis finds the delta cores softening, the polarities beginning their long drift apart, the area holding steady or shrinking instead of growing. A day later, the forecast probabilities step down. 50% M becomes 30, becomes 15, and region 4493 joins its predecessors from this remarkable July, as one more monster that burned for 3 days and went out right on schedule. If this is the ending, it arrives undramatically. You will simply notice, checking the feeds tomorrow evening, that nothing has happened for a while. The pattern will have held 4 times in 4 tries, and that itself would be quietly important. Every clean repetition strengthens the case that these fast-emerging dominant regions really do follow a script, and a script once trusted is the seed of an actual forecasting tool. The most valuable thing the sun could give science this week might be an uneventful Thursday. Ending 2. The Flash. At some unknowable hour inside the window, one of those welded cores reaches its threshold, the cage gives way, and the instruments light up. X-ray flux spiking through the M range into X territory, an R3 blackout sweeping whichever hemisphere faces the sun at that minute. Aircraft on polar routes rerouting toward lower latitudes, high-frequency bands dead for an hour or more across half the planet. Then, within the following hour, the chronograph images that tell us whether the flash carried a payload, a halo, expanding evenly in all directions around the blotted-out sun, the ring of light that means this one is ours. Modelers would fix its speed and departure, the world would get its 1 to 3 day heads up, and somewhere in the arrival estimate would sit the extra uncertainty of the churned-up river the projectile must cross, the stream, the wakes, the traffic you now understand. What lands at the far end of that crossing could be anything from a vivid aurora night to the most serious geomagnetic test in years, and we would cover every hour of it with exactly the calibration this video has tried to model. Severity from data, not from volume. Between those endings runs every intermediate path, more M-flares that keep the cage rattling without breaking it, a partial eruption blunted by the stream, a late surge after a deceptive lull. and the map for tracking which path unfolds fits in one paragraph. So here is your watch list for the next 36 hours. Tonight, 2100 Universal Time to midnight. The stream arrives. Expect the planetary index to climb toward 5, the official G1. If you're far enough north, look for aurora after local midnight, twilight permitting. Through tomorrow, the stream storm tapers while the region's flare drumbeat either slows, the fade beginning, or does not. Tomorrow's forecast discussion, and the next day's, the region analysis lines about growth, consolidation, and those delta configurations are the plainest single indicator in public data of whether the window is closing quietly. Late July 23rd, the low-confidence possibility of a glancing shove from the July 20th ejections, and the pending verdict on yesterday's faint filament release, the first candidate projectile of this region's life, still unresolved as of tonight, and running under all of it, the one number that summarizes the entire vigil, 10% per day, compounding toward 1 in 4 until geometry finally carries the region off target around July 25th or 26th. There is a third shape worth sketching too, because the sun loves the ambiguous middle, the week that ends without a verdict. In this version, the region keeps firing M-flares past the pattern's deadline, enough to keep the blackout forecast pinned at 55%, enough to keep the drumbeat alive, but the cage holds, no halo ever blooms, and the classification tables refuse to budge in either direction. Day 4 arrives with the region still growing, still contained, still aimed at us, and the window simply extends, with geometry now doing the diffusing that the pattern promised and did not deliver. If that is where we are on Friday, the story becomes the pattern itself. 4 regions, 3 clean fades, 1 refusal, and the 3-day rule quietly demoted from clock to tendency. Watch also for the small print resolving underneath, the faint filament ejections verdict, which if Earth-directed would announce itself as a modest flutter in the solar wind data around July 24th. A brief kink in speed and field, the kind of signature only people who know to look for it ever notice. You now know to look for it. And because a vigil is more interesting with your own eyes on the instruments, here is precisely what each signature would look like in the public data, so you can recognize the verdict the moment it renders. The fade announces itself in absences, the X-ray plot flattening, its between-flare baseline sinking from the C-range murmur down toward B levels, hour after uneventful hour. The region analysis line is the confirmation. Watch for the day the magnetic classification drops the word delta. The moment the welds officially soften, the probabilities follow that letter downward within a day. The flash, by contrast, is unmistakable in 3 acts. The spike on the X-ray plot climbing past the M-range ceiling into X territory, then, within the hour, the blackout maps lighting up the sunlit hemisphere, then the chronograph frames updated every several minutes publicly, showing either a directional puff angled harmlessly away or the expanding ring of a halo. If you see that ring, you will know what the following 2 days hold before any headline tells you. The arrival watch, the upstream sentinel's final hour of warning, and a storm whose strength comes down to the coin flip orientation of a magnetic field nobody can read until it is nearly here. 2 shapes in the data. One of them is coming this week. Whatever the sun decides, I want to leave you with the thought this whole strange July has been building toward. 3 times in 4 weeks now, this star, supposedly relaxing into the quiet half of its cycle, has assembled a giant from nothing in a matter of hours, aimed it at us by pure rotational chance, and made the best minds in the field admit they cannot say what it will do next. We have wrapped the sun in more instrumentation than any object in the sky. We have upstream sentinels tasting its wind an hour before it touches us, observatories photographing its surface every few seconds, a global forecasting institution born from the day it nearly tricked us into ending ourselves, and still on the only question that matters this week, will it fire? All of that machinery can offer only honest odds. The sun remains what it was in 1859, in 1942, in 1967, the one force in our sky that we can watch perfectly and predict barely, a neighbour whose moods we have learned to read but never to anticipate, the star that gives this channel its name and this planet its weather in both senses of the word. 59 years ago, we survived our own blindness by the width of one good forecast. Tonight, eyes everywhere, we wait on a 2-day-old knot of magnetism to reveal which kind of week this becomes. And the beautiful, maddening truth is that the region has already decided, in the sense that its field either holds the strain or it does not, and the only party in the universe not yet informed is us. The window is open. Somewhere around the far side of tomorrow night it closes, one way or the other. And when tomorrow's region analysis publishes, the first data point of the verdict will be sitting in one quiet line about whether those delta cores held their grip overnight. Whether that line reads like a fade or a fuse, that is the question we will be waiting on right here when the sun shows its hand